So in the last lesson of the chapter, we are looking at some relationships between chords, diameters, and tangents, and how they're related, how they may be congruent or perpendicular. And we have some theorems today that tell us different pieces about those parts of a circle. So our first vocabulary word is, or are, congruent circles. Congruent circles will have congruent radii. Remember, there's only one dimension of a circle, so if the radius is congruent to the radius, then they are congruent circles. So within a circle, or in congruent circles, there's three things that we can learn from one of the theorems. The congruent central angles will have congruent chords that can be drawn. So before we move on, let's look at the picture. An example of a central angle would be angle AEB. That will be congruent to angle DEC. Why? Those are vertical angles. Okay, those are also central angles. They're congruent. So if you know that the two angles are congruent, you can conclude that the two chords that are like enclosed by the angle would be congruent. So we would be able to see that segment DC is congruent to segment AB. I'll put a little congruent marking on there. Now, if you know you have congruent chords, then you'll also have congruent arcs. So congruent chords will have congruent arcs. So that would mean that arc DC is congruent to arc AB. And then it kind of just goes cyclical back to the beginning. If you have congruent arcs, then you have congruent central angles. So basically, if you're given any one of the three things, you can conclude the other two. So if I tell you the chords are congruent, you could tell me the arcs are congruent and the angles are congruent. If I tell you the arcs are congruent, you can tell me the chords and the angles. If I tell you the angles, you can tell me the chords and the arcs. So knowing just one of those things, you can then conclude two other pieces based on these theorems. All right. Another theorem says within a circle or in congruent circles, chords equidistant from the center are also going to be congruent. Remember that equidistant just means equal distant from. So you can see in this picture we have two chords. We're shown that they are the same distance away from the center, which means that the chords themselves will be the same length, will be congruent. And then the other one's the converse, which says if the chords are congruent, then they have to be equidistant from the center. And then we have three more theorems moving down about diameters and chords and their intersections. Remember, diameter is a segment that goes through the center and touches both sides. A chord just has 2 points on the circle. So we have three theorems here. So in a circle, a diameter that is perpendicular to a chord is going to bisect. Throwback word, what's that mean? Bisect? Nope, that would be perpendicular. Yes, it will go through the midpoint. It's going to cut it into two congruent segments. So if you know that the diameter and the chord are perpendicular, so you have to be given that they're perpendicular, then you can conclude that it is a perpendicular bisector, actually. The next one is the converse of this theorem. So it says, if you know a diameter bisects a chord, then it has to be perpendicular. So just going in the reverse, which is called our converse theorem. I didn't put the numbers with these because remember the numbers aren't relevant to the theorems, but just the content. And the last one kind of relates to this. It tells us in a circle, the perpendicular bisector of a chord. So if you know that you have something intersecting two segments and they are perpendicular and bisecting, then that tells you that it has to be a diameter, meaning it has to be going through the center of the circle. And then we have two more theorems, and then we'll just apply these to problems, which a lot of them are congruent, so like, you'll see how easy they are. You're just copying numbers around the sheet. Okay, we have two more theorems about our tangents, which it looks like I got cut off a little bit. And I already kind of talked about this when I introduced the tangent. It says if a line is tangent to a circle, then the line is going to be perpendicular to the radius drawn at the point of tangency. So whenever we went over this vocabulary word, I kind of showed you how the radius, remember the tangent is a line that just like grazes and barely nicks the edge of the circle, just at one point, called the point of tangency. This will be perpendicular to the radius. And then the last one, did this get cut off on your paper? Yeah? Just kind of fill it in. It should be a circle. And then you'll have two segments coming off of it. They're two tangents. Kind of looks like a cone, like an ice cream cone. So this says the two segments that are tangent to a circle to a point outside the circle, so like an outside angle, are equidistant. From the point of tangency. Could also think of them as being congruent. So I think this is supposed to have an A next to it. We would say that AB is congruent to BC. So when you have two tangents intersecting outside, the tangents will be equidistant from the points of tangency. All right, now we're just going to apply those to some problems. Again, most of them are really quick, not any work required, but the circles are congruent. What can you conclude? So this is reaching back to the front when we had our three things. If we have congruent central angles, then we have congruent chords. If we have congruent chords, then we have congruent arcs. If we have congruent arcs, then we have congruent central angles. So again, you just need one of those three things, and you can come up with the other two. So in this picture, they give us that we have congruent central angles. So it's central angles, chords, and arcs. So we're given central angles, so I'm not going to write that. But from this, I can conclude that the chords are congruent. So BC is congruent to YZ. And since we have congruent chords, we have congruent arcs. So arc BC will be congruent to arc YZ. And we'll use two letters because it's a minor arc. Now the next one, we actually have two central angles given. But what are these types of angles? So you actually know that these are congruent also. So you actually have four angles that are congruent to one another. So remember, we go from central angles to chords, which means this chord will be congruent to this chord and this chord and this chord. So we're going to write a big, long congruent statement. We're going to say that segment TE is congruent to segment HG, which is also congruent to JN, which is also congruent to ML. And this is all because we have vertical angles which end up creating 4 congruent angles instead of over here, we just had 2. So we have 1, 2, 3, 4, therefore we should have 4 congruent chords. So we have central angles, we have chords, now we can attach our arcs, which is going to be the same letters. Arc TE will be congruent to arc HG, excuse me, which will be congruent to arc JN and ML. So the 3 things you need to remember are central angles, then chords, then arcs. If you're given any of these 3, you can list the other 2. All right, the rest of them are looking at our equidistant theorem, which had said if a chord is equidistant from the center, which we can see they're 5 and 5, so they're the same distance, then the chords are congruent. So what that means is we can see markings that this is 7, which means this is also 7, so the whole chord is 14. This chord has to be congruent to that, so x has to be 14. Again, to see equidistant, equal distance, they're either going to give you numbers showing you they're the same number, or they're going to put markings to show that they're the same distance. They're congruent. So what do you think the value of x would be in this one? Ready? 10. If this is 5, this is 5, the whole thing's 10. The chords have to be congruent, so this also has to be 10. These are working with the converse theorem. So you can see that the chords are congruent. We have 5 and 5. So if the chords are congruent, then they have to be equidistant from the center. So what would x have to be? Marquise? 2. It has to be the same distance away. And then how about 6? What do we think the answer for x would be? Maybe someone I haven't heard from yet today. Right?
X equals 8.
Yes. You can see the chords are congruent by the markings, so they have to be equidistant. So they have to be 8 and 8. All right, we're going to make these a little bit harder. Does yours say 3.6 on it, or does it say 6? All right, change this to 6. We're going to make the problem a little bit easier. But let's do 7 first. I just figured in case anyone's working ahead. So in this one, we can see that they are equidistant. So that means the chords are congruent. So what is x going to be? Kale?
25.
Did you say 25?
Yeah.
25 is only half of the chord.
So that's 50.
Yep. Yeah, since they give you this little piece and they tell you these are congruent, then you can double it, add them together. All right, now this problem looks confusing. First of all, we learned a theorem, let's go back, that says, oh, back one more page. If a diameter is perpendicular, that it has to be bisected. So in this picture, they actually give you a radius, right? But you could, oh no, they don't give us a radius. It doesn't go all the way up. But we could draw it past. So you can see that it could go up. Could be a diameter. If it's perpendicular, then it has to bisect. So let's go ahead and mark this as half and half. And if the whole thing's 8, that means that each of these are 4. Now, the radius is x units long, and that's what we're looking for. Remember that a radius can be drawn anywhere, right? So for this one, you're actually going to move the radius to create a right triangle. So you can swing this radius wherever you need to, and it'll still be x units long to help you. So I'm going to take this radius, I'm going to move it here. it's still x units long. Now, how can we find x? We have a right triangle, we know two legs. Right? Pythagorean theorem. I should have changed it to like 3, and then we could have done a triple, but no. So we have a right triangle, 4, 6, and x. So 4 squared plus 6 squared equals x squared. And let's just practice leaving this in simplest radical form because you're going to see some of that on your final again. So we'll square each number. We'll add them together to get 52.
4 squared is 16.
Thank you. I have it on my paper. And I just realized when I add this, it didn't give me 52. All right. 16 plus 36 gets me my 52. There. And then we would square root. Let's simplify this. What can I write 52 down into? One of them being a perfect square. 1, 4, 9, 16, 25. More. Maddie? Yes, that'll be my final answer. I will break this into the square root of 4 times the square root of 13, and then what Maddie did was took the square root of 4 and got 2 root 13. We didn't have any units, so don't worry about units. All right, so for this one, we're given a diameter is 20. So the first thing we want to do is cut that in half to get 10 and 10. And again, since we know that this is perpendicular to the chord, it has to cut the chord in half by our theorem. So this would become 8 and 8. And then we can use Pythagorean theorem again. Or a triple, should be 6. This would be a 3, 4, 5 times 2, which gets me my 6, 8, 10. Making sure 10 is the hypotenuse. Otherwise, you would do your Pythagorean theorem. Now the next one, we're going to do Pythagorean theorem, but here's the problem. X is the length of the whole thing. So you cannot do x squared plus 4 squared equals 6 squared, because x is not this length, it's this. So you have two options. You can either let this represent 1/2 x, and then that'll find out what x is. Or what a lot of students prefer to do is define a new variable, like y. Do the Pythagorean theorem with y, and then at the end, double your answer to get what x is. This is probably the preferable method, otherwise you have to do some work with square roots and stuff. So let's do this. We'll have our y squared plus 4 squared equals 6 squared. Subtract. Square root. Now let's do simplest radical form again. So what would this be in simplest radical form? Brett?
8, or y equals 5 root
Other way around.
3. Or 2 root 5.
2 root 5. So this would be the square root of 4 times the square root of 5. So it will be 2 root 5. So that's y. So then all we have to do at the end of that problem is double it to get what x is. We do not double the 5, just the 2, because it's really 2 root 5 plus 2 root 5, which will get me 4 root 5. But if you want to multiply, you're only multiplying that outside number. You will get x equals 4 root 5. Okay. Next, you deal with our tangents. So we're going to switch from chords to our tangents. Okay. You just need to remember that if a tangent is intersecting the circle, it's going to be perpendicular to the radius or the diameter. So if you know that this is a tangent, it's just grazing that circle, you can put in a right angle box. And then how would we find x? No? Easier than that. Yeah? Triangle sum. We know two angles, we need to find the third. So we'll just take 180 minus 90 minus 43. And we'll get 47. But if you don't remember to put the right angle box in, you're going to be having no idea how to do it. So you need to memorize that the tangent is perpendicular to the radius or the diameter. Now in this instance, I have two tangents. We have a tangent here, and we have a tangent here. Which means we can put a right angle here and here. Now last time we did triangle sum because it formed a triangle. What shape is this? What? It kind of looks like a kite, yes. But just in general, 4 sides is a quadrilateral. So we can do quad sum. It would be a kite, actually. Yes, it would, because we would have these two sides being congruent because they're radii, and we learned a theorem that said the tangents are congruent. It's technically a kite. But we would do quad sum, which is 360 minus 90, and minus 60. And we should get 120. If you forget to put these in, again, you're not going to have any idea how to solve the problem. You're going to sit there and just be like, I don't know. So you have to memorize the tangent and the radius, right angle. Okay? 13 and 14 just ask us, they give us all 3 sides. They say, determine whether a tangent line is shown. So you're just testing, tangent line has to be perpendicular. So you're testing, is this a right angle? AKA, is this a right triangle? So you just have to test to make sure that the Pythagorean theorem does work. So you're just going to check, is this a right triangle? So does 6 squared plus 8 squared equal 10 squared? And we're not sure. It does. It's a triple. So you can just say yes. But you would get 100 equals 100. Again, make sure you put the right angle in so you know like what's your legs and what's your hypotenuse. We're checking, is this a right angle? So we're checking, is 5 squared plus 15 squared, question mark, does that equal 16 squared? And when we do 5 squared plus 15 squared, that'll be 225 plus 25, which will be 250. 16 squared is 256. So those are not equal. So the answer is no, this is not a tangent because it's not a right angle. So even though it looks like a tangent, it's not. And then we have 2 problems to finish out with our last theorem, which was when we have 2 tangents. So if you remember, we had the circle and we had our tangent and our tangent, and I said that the tangents would always be equidistant from the points of tangency. So I always say for these problems, because they put a lot of them, first of all, they look to be congruent, but if you think about like an ice cream cone, the 2 sides of the ice cream cone have to be the same length to hold up the ice cream, otherwise like if it was lopsided, the ice cream would fall out. So if you look at this as being like the cone, these would be congruent. Those will be congruent. Those little ones will be congruent. And lastly, those will be congruent. They look to be congruent, like the ones you're picking. So they want us to, they say each polygon circumscribes a circle, which means that it's just outside the shape. Find the perimeter of the polygon. So you just have to make sure that you put the right numbers in the right spot. So if this is 16, this is 16. This is 9, this is 9. 6 and 6, and 8 and 8. And all we have to do is add up all the numbers. So we'll literally add 8 plus 8, 16 plus 16, 9 plus 9, and 6 plus 6. should get 78. Now the last one, 16, we're not gonna do the closure, is a little bit harder because they don't give you all the little pieces. So you wanna start with this 1.9. Which other part would be 1.9? This part or this part? The left or the right? Marquise? The right. Now if you know this whole thing is 3.4, we can subtract those. So 3.4 minus 1.9 will tell me that this little piece is 1.5. And remember, these two sides, these two tangents have to be equidistant, so this is also 1.5. So these are congruent, these are congruent. Now we subtract 3.6 minus 1.5 and we'll get 2.1. If this is 2.1, the other side of the ice cream cone is 2.1. And then lastly, you can subtract those, 3.7 minus 2.1 to get our 1.6. And then you would sum up all of those sides. The only way that you can really screw this one up is if you put the 1.9 here by accident. But just remember that they have to go around, so then we just subtract it. The final answer there was 14.2.